Hello, this is Kelly Freeman with A Plus College Ready, and I'm here today to talk to you about, or introduce you to, the first unit in the curriculum called Introduction to Chemistry. Chemistry is the study of matter. There are two main physical sciences, chemistry and physics. Chemistry being the study of matter and physics being the study of energy, and so put the two sciences together and you cover the entire universe. Matter is anything that takes up space and has mass. Matter takes three different forms: solid, liquid, and gas, with solids having the least energy and gases having the greatest energy. You can compare these states of matter to a soccer field. The fans in the stands represent a solid. They're closely packed together and their motion is vibrating. They're standing in place, but they're still moving, much like the molecules or the particles in a solid. The people walking around the track that encircle the field are like liquids. They have a fluid movement. They're connected, they're together, but they're moving much in the same direction, more around one another. More movement than the vibrations. And finally, the players on the field are like gases. They have the greatest movement, bounce off of each other, have the greatest distance between them. So solids have a definite volume and a definite shape, while liquids have a definite volume but take the shape of their container. And finally, gases take the shape of their container also. They have no definite volume and no definite shape. Most energy, least energy. So let's talk about some lab equipment, some common pieces of lab equipment. There is a resource in the curriculum that gives you a much bigger scope of equipment that you might use in the laboratory. Here in the PowerPoint, I've tried to introduce you to pieces of lab equipment that you would be most likely to use in the laboratory. So the beaker is used to store reagents and liquids. It gives a good estimate of volume, but it should not be used when you need to be accurate about your measurement. It gives you a good estimate of volume, but not an accurate measurement of volume. Mostly used to contain and store liquids. The Erlenmeyer flask is also has a common use in terms of like the beaker. Additional advantage of the Erlenmeyer flask is that the shape allows for easy mixing or swirling. You can also easily seal an Erlenmeyer flask, but it also should not be used to measure liquids, only an estimate of the volume of liquids. The graduated cylinder, however, is a very precise piece of glassware and should be used when you need to get an accurate reading, a certain reading of volume of liquids. The evaporating dish is used to hold or store solids. It is ceramic, and most pieces of ceramic lab equipment can take a higher heat than glass. The Bunsen burner is used in the laboratory to heat substances. The wash bottle is used to wash down chemicals into glassware. You have a Flynn safety contract that goes into great detail about important safety issues in the laboratory. Some of the safety issues I wanted to address here include always wear goggles and aprons. Always wear shoes that cover the entire foot. Always waft reagents. Never smell them directly. You should never point an open test tube toward another student or yourself. If you have long hair, it should be pulled back in the laboratory. Certainly never eat or drink in the laboratory. And always wash your hands after the lab. So here we have a picture of some students who are operating in the laboratory, and let's see if we can find some things that they're doing correctly and some things that they are not doing correctly. So let's look at things that they're doing well. So for example, this young lady and this gentleman, and it looks like maybe this young woman all have aprons on. That's a good thing. That's what we should do in the laboratory. It looks like this young man might be washing his hands, certainly washing a piece of equipment, but maybe washing his hands. That's always a good thing. But let's also look at some things that are not done well in the laboratory and that might be a safety issue. I don't see goggles on this young man, nor on this young woman. In fact, I don't see goggles on any of the students. This student has her hair, even though she's using a Bunsen burner, her hair is not pulled back. That's going to be a safety issue. This student is eating in the laboratory, should never ever eat or drink in the laboratory. This student has a test tube certainly pointing away from him, but potentially could be a problem if something in the test tube explodes and hits his friend, a safety issue. The scientific method is a methodical problem-solving process that includes observation, and then from that observation, formation of a question, development of a hypothesis to address the question, experimentation and collection of data, and the analysis of data to form a conclusion. And finally, the repeating of this process until you're sure that you get the same results over and over again. Scientific method is probably something you've been exposed to by the time you've gotten to a chemistry class. Certainly a very common problem-solving process. All of us use the scientific method, and even in our everyday problem-solving situations. A hypothesis reflects a testable statement. It must be measurable and is often, but not always, related in an if-then format. A data chart should be built around the type of data you need to collect. It should be clearly labeled, and all units should be provided. You should only document what you observe, measure, or observe. That is data. Only data goes in a data chart. Analysis of the data should be done somewhere else in your lab report, maybe under analysis, but a manipulation of data should not be done in a data chart. Only what you observe or measure in the laboratory. Analysis is done using the data that was gathered. Analysis can take the form of a narrative, or calculations and manipulations of the data, or maybe most frequently, graphing of that data. Graphs of data frequently include a dependent, y, variable and an independent, or x, variable. The independent variables are factors that can be changed on purpose, while the dependent variables are the factors that changes as a result. Here's an example. We have a hypothesis. How will increasing the drop height of a ball in 2-meter increments affect the height of the ball bounce after it hits the ground? So this is a testable statement. This is our hypothesis. This is our independent variable. That's the variable we're going to change on purpose. And here is our dependent variable. That's the variable that's going to change as a result of changing the independent variable. The dependent variable depends upon the independent variable. So you try it. Write a hypothesis for each of the following questions, then identify the dependent and the independent variable. What effect does increase in temperature have on the growth of radishes? One hypothesis might be, if temperatures are increased, the growth of radishes will increase. Here's the independent variable. This is the dependent variable. The dependent variable depends upon the change in the independent variable. What effect does studying with music have on student test scores? So if music is played during study time, student test scores will increase is one appropriate hypothesis. The dependent variable depends upon the independent variable. The periodic table is a tool you'll be using throughout chemistry. It will become more and more important. You will always have access to a periodic table in your chemistry class. You will learn about the periodic table more in depth in other units of chemistry. Here I want to give you some very basic ground rules about the table so that you can begin to use it appropriately. So there's a stair-step line on the periodic table that separates the metals from the nonmetals. So to the left of this stair-step line are all the metals, and to the right of the line are the nonmetals. This is going to become very, very important when you reach bonding and nomenclature to be able to tell a metal from a nonmetal by looking at the periodic table. Groups or families are columns going down the periodic table. There are 18 groups or families. Periods are the rows that are going across. There are 7 periods on the periodic table. You should take time after this PowerPoint to mark your stair-step line on your periodic table and to label the groups 1 through 18 across and 1 through 7 down on your periodic table. Groups are called families because the elements within that group have similar chemical properties. Group 1, the groups on the periodic table have some other names that you need to be familiar with. Group 1 are called the alkali metals. Group 2 are called the alkaline earth metals. Group 3 through 12, that block that drops down in the periodic table, are called the transition metals. Group 17 are the halogens, the most reactive nonmetals on the periodic table. And group 18 are the noble gases. These are gases that are very unlikely to react with the other elements on the periodic table. Chemical symbols have 1 or 2 letters. The second letter must always be a lowercase, while the first one is an uppercase. Some elements have Greek, Latin, or German origins. For example, sodium is from the Latin natrium. Sodium, Na, comes from this Latin word. It's important that you use a lowercase for that second letter. For example, this is a compound called carbon monoxide, while this is an element called cobalt. So there's a great deal of difference in just making sure that you have the lowercase letter for the second letter. So matter can be classified or categorized into elements, compounds, and mixtures. Elements are pure substances that cannot be broken down into smaller units and still possess their chemical properties. The smallest unit of an element is the atom. An example of an element would be anything on the periodic table. For example, gold or hydrogen are elements. Compounds are substances made of 2 or more different elements bound together. Some examples include water, two atoms of hydrogen to 1 atom of oxygen, or sodium chloride or table salt, 1 atom of sodium to 1 atom of chlorine. Mixtures are made up of 2 or more substances that are physically mixed but not chemically combined. Mixtures can be further separated into heterogeneous or not uniform substances and homogeneous or uniform substances. Heterogeneous compounds are easily separated. An example of a heterogeneous compound, a heterogeneous mixture, not a compound, is a pizza. Pizza is made up of substances that are physically mixed but not chemically combined. I can take the pepperoni off the pizza, I can take the olives off, I can remove the cheese. I can easily separate these components. This is a heterogeneous mixture. A homogeneous mixture is more difficult to separate. Possible, but more difficult to separate. And it has a uniform substance. An example of a homogeneous mixture is a solution of any kind. For example, salt water. Salt water is a solution. It's a mixture of water and salt. Now, we can't reach into salt water and take out the salt, but if we evaporate the water, the salt remains at the bottom. So the salt and water was physically mixed, but not chemically combined. So these are particulate drawings of elements, compounds, and mixtures. Particulate drawings are very important on the AP exam. You will need to be able to interpret particulate drawings, and sometimes you'll be asked to draw particulate drawings. Notice that the particulate drawing for an element here is oxygen. Here we have the same type of atom, which is part of the necessity of being an element, but we have two of these atoms that are chemically combined. The fact that they're not different makes this an element and not a compound. This is a special type of element called diatomic element, and because we have these two atoms bound together, we would call this a molecule. The compound has two or more different elements chemically combined. Here we have a particulate drawing of water where we have the oxygen as one element and two atoms of hydrogen as the second element. So here we have 1, 2, 3, 4, 5, 6, 7, 8 molecules of water, and in any one molecule we have 3 atoms of 2 different types. Over here we have a mixture of salt water. Here we have the water molecule, which is a compound of 2 different types of elements chemically bound together. And what we have here is a particular type of particle called an ion. It comes from an ionic compound called sodium chloride. The compound has been pulled apart, and now we have a charged particle called an ion. This would be the chloride ion, while this would be the sodium ion. So let's put this to work. Here I have 4 diagrams, 4 different particulate drawings. Is X an element, a compound, or a mixture of elements and or compounds? X is an element. It's an element because all the particles are of the same type, and they're not chemically bound to another type of an atom. There are 4 atoms of this element in the box. Is Y an element, a compound, or a mixture of an element and or a compound? Y is a compound. You have 2 or more elements that are chemically bound together. There are 1, 2, 3, 4, 5, 6 molecules. This is wrong. Maybe 6 molecules of this compound in the box. For any one compound, I have 2 atoms in that compound of different types. So I have a total of 12 atoms in this box. Is Z an element, a compound, or a mixture of elements and or compounds? Z is a compound also, 2 or more elements chemically bound together. There are 1, 2, 3, 4, 5 molecules in this box. Any one molecule is made up of 3 different types of atoms. For every one molecule, we have 3, and we have 5 molecules, so there are a total of 15 atoms in this box. Is W an element, compound, or a mixture of elements and/or compounds? W is a mixture of elements and compounds. There are 2 molecules of one type of compound, here and here, and 1 molecule of another type of compound, here. And then we have 3 atoms of an element. This compound has 3 different types of atoms. This compound has 2 different types of atoms. So there are a total of 10 atoms in this box, and 1, 2, 3, 4, 5, 6 different types of atoms. Let's talk about how you go about separating mixtures. This is a common methodology in any type of lab. You've got to be able to separate a mixture in order to determine what are the components of that mixture. We're going to talk about filtration, evaporation, distillation, and chromatography, with chromatography being maybe the most important. Filtration is separation using differences in size of particles. It's also used to separate an insoluble substance and a liquid. In this case, we have sand and water. So here is the sand being collected in the bottom. This is the insoluble substance that we're talking about, sand, which has been mixed in with some water. And we're using the idea that water molecules are so much smaller and are able to come through the filter paper, while the sand particles are so much larger and are stopped by the filter paper. Evaporation is used to separate a dissolved solid and a liquid. For example, salt water again, we've talked about that once before. If you wanted to separate the salt from the water in a saltwater solution, you simply evaporate the water away. Salt is left at the bottom. Distillation is the separation of 2 or more liquids based on differences in boiling points. This is a good way to separate 2 liquids that have been mixed together. And the best example of this is really a moonshine still. So we've got a moonshine still here, and in it we have water. We start with a lot of water and some yeast and something for the yeast to eat, like corn or other kind of grain. And as time goes by, as the yeast consume the corn, they manufacture alcohol. But unfortunately, that alcohol is mixed in with the water, and that won't do. So we need to separate the alcohol from the water. We heat this moonshine still, and we use the fact that alcohol has a lower boiling point than water, and as we apply the heat to the still, the alcohol is going to boil off first. It's going to evaporate, go into a gas, going to run it through a cooling coil, and it's going to drip out. And once we separate all the alcohol, this drip will stop, and if we continue to heat it, the water will come off too. But if you know how to run a good moonshine still, you'll stop that heating before the water comes off. Chromatography is the separation of dissolved substances based on a degree of solubility. Very common methodology in all types of labs. This is actually a paper chromatography, which I hope you will do in laboratory. If we use a substance like inks from magic markers, we can put them here and here, and if they're water-soluble inks, we can dip our paper into a solvent like water. The water will travel up the paper. It will dissolve these inks that we've put here, and the different colors in the inks will separate based upon their degree of solubility, with the color being the most soluble traveling the farthest up the medium, and the color being the least soluble, being the one that is closest to the solvent. So it's a very, very good way to separate substance based on their degree of solubility. Physical and chemical properties. Physical properties are observed without changing the composition of a substance. For example, melting points, boiling points, and densities. Chemical properties are observed as a substance undergoes a change in composition. An example of a chemical property is flammability. So in terms of physical changes in physical properties, the way you tell the difference between the two is you ask yourself this question: has a new substance been formed? Or do I have really the same thing after the change, just in a different format or in a different way of looking at it? So if you have some liquid water and you freeze it so that you have ice, you really have water on both sides. You have water that's liquid on one side, you have water that's solid on the other side, but you have water both before and after the change. That's a physical change. But if you cook a cake, if you start with flour and milk and eggs and you mix it all together and then you put it in the oven, on the other side you have something completely new. You don't have flour and milk and eggs anymore. You have a cake. What's happened is we have a chemical change. If you have a piece of wood and you burn it, at the other end of that burn, at the end of that burn, you have what is left of the log in terms of ashes and CO2 and smoke. You have something completely different. That's a chemical change. So, cutting bread, slicing bread, is that a physical or a chemical change? That is a physical change. The substance is the same or before and after. We've changed the form. It's smaller, but it's still bread. Bread before, bread after. What about rusting of nails? Is that a chemical or a physical change? This is a chemical change. The iron that makes up the nails has been exposed to oxygen. That iron has reacted with the oxygen in the air to form a brand new substance called rust or iron oxide. The iron oxide is no longer iron or oxygen. We have a brand new substance. This is a chemical change. Intensive and extensive and intensive properties. Extensive properties depend on the amount of matter in a sample, such as mass or volume. Intensive properties do not depend on the amount of matter in a substance, such as temperature, solubility, or density. A small piece of copper is just as dense as a large piece of copper. We're going to talk about this more extensively in the scientific math PowerPoint. Finally, let's talk about exothermic and endothermic. Endothermic reactions are reactions that absorb heat, pull heat from the surroundings into the system. They appear on the left side. If you write a chemical reaction, they appear on the left side of the chemical reaction, on the reactant side of the chemical reaction, the endothermic. Endothermic reactions feel cool to the touch. Exothermic reactions release heat from the system, from the reaction to the surroundings. Heat, if you write the reaction, appears on the right side of a chemical reaction. Here are the reactants, here are the products. Heat is given off in an exothermic reaction. Heat is absorbed in an endothermic reaction. Exothermic reactions feel warm to the touch. This is very important to remember in terms of exo and endothermic reactions, and this will help you as you go through thermochemistry in AP chemistry, and if you take AP biology, also help you there if you keep this in mind. Exothermic reactions are about the formation of new bonds. The formation of bonds releases energy. So as you make new bonds, as you go from reactants to products here, as you go from reactants to products here, and you're forming new bonds here, energy is released out of that reaction, feeling warm to the touch. The breaking of bonds requires energy. So if these are the reactants and these are the products, and energy comes in, we use that energy to break these bonds. That requires energy. So during an exothermic process, less energy is required to break the reactant bonds than the energy that's released to the surroundings when product bonds are formed. So let's talk about that. Let's think about that. So we have reactants moving to products. During an exothermic reaction, less energy goes in to break the reactant bonds than is energy that is released when the product bonds are formed. So if we look at the net energy, we have energy going out. Energy came in to break, energy went out when formed, but more energy went out than came in. Exothermic. In an endothermic process, more energy is required to break the reactant bonds than is released when product bonds are formed. So let's look at our diagram again. If we've got reactants and products, for an endothermic reaction, more energy was required to break the reactant bonds than was released when the product bonds were formed. So we look at the net energy again. More energy had to come in to break the bonds than was released when the bonds were formed, therefore resulting in an endothermic process. These are called energy curves, and you will see them in your AP class quite frequently, and also in your AP biology class. So if these are the reactants here, and these are the products, and we start here and we put energy into the reaction in order to get it to go, called the activation energy. Reaction happens and the reactants bonds are broken. They're reformed over here as products. What happens is the products end up having more energy than the reactants. Energy has to come in. More energy was required to break these reactant bonds than was released by the products, therefore endothermic reaction. Here's an exothermic reaction. Here are the reactants. Here are the products. Energy did have to come in to break those reactant bonds, but as the reaction proceeds from reactants to products, energy is released from the system, from the reaction to the surroundings, because more energy was released when the product bonds were formed than was required to break the reactant bonds.